Picture this. You board a spacecraft right now, lock in coordinates for Andromeda, and launch. Here's what happens next. You don't make it, obviously. But it's worse than that. You die. Your entire species dies out. The sun runs out of fuel and collapses. Earth disintegrates into cosmic debris. And your spacecraft? Still nowhere even remotely close to the destination. Most people figure we'll crack intergalactic travel eventually, build some next-gen propulsion system, give it a slick designation, and boom, off to explore. That's wishful thinking. Even calling it travel is generous. It's like calling a single water molecule a river. Here's the reality. The gap between us and Andromeda is so enormous our brains literally cannot process it. But we can try anyway. Andromeda is the nearest large galaxy to the Milky Way. Not the closest celestial body, plenty of stars are closer, but the nearest galaxy of similar size. Distance? About 2.5 million light-years. Sounds almost reasonable until you understand what a light-year represents. It's not time, it's pure distance. How far light travels across one full year. And light moves faster than anything in existence, 300,000 kilometers every single second. One light-year works out to approximately 9.5 trillion kilometers. Take that figure and multiply by 2.5 million. The result is around 24 quintillion kilometers, a 24 followed by 18 zeros. Your brain doesn't have the capacity to imagine that. Mine doesn't either. It's equivalent to trying to mentally picture every water molecule in the Atlantic Ocean. When astronomers tell us Andromeda sits 2.5 million light-years away, they're essentially saying it's unfathomably, absurdly distant. Humanity's speed record belongs to NASA's Parker Solar Probe. That machine screams through the void at approximately 700,000 kilometers per hour, quick enough to lap Earth in under 180 seconds. Pretty damn fast. But here's the kicker. At that velocity, reaching Andromeda would require about 4 trillion years. For reference, our universe has existed for roughly 13.8 billion years. You'd need around 300 times the entire lifespan of reality. By the time your ship reached the midpoint, galaxies would have collided and reformed, stars would have extinguished, and Earth would be nothing but scattered atoms floating in dead space. So what if we ramped up the speed significantly? Imagine constructing a vessel capable of 10% light speed, about 30,000 kilometers per second. Sounds insane, right? Even at that blistering pace, the journey would consume 25 million years. 25 million years. For perspective, 25 million years back, humans didn't exist on Earth. Our evolutionary ancestors were primates living in trees. If they'd miraculously built a starship at that point and launched it toward Andromeda, it still wouldn't have arrived today. That's the magnitude we're confronting. But what if we pushed to the absolute limit? Fine, let's throw physics out the window. Say you somehow accelerated to light speed itself. You'd complete the trip in 2.5 million years. Still sounds nightmarish, and it's also fundamentally impossible. Objects with mass cannot reach light speed. As you accelerate, your energy increases and your effective mass increases along with it. Hitting light speed would demand infinite energy. Infinite energy doesn't exist in our universe. It's like trying to fill a bottomless container. You can conceptualize it mathematically, but you cannot execute it. What about the science fiction shortcuts? This is typically when people mention warp drives or wormholes. All right, let's break them down. Warp drives, like Star Trek technology, don't technically accelerate you past light speed. They bend space-time itself, contracting the distance between two locations. You're not going faster, you're collapsing the distance. Clever concept, major problem. You'd require a preposterous quantity of energy to achieve it. More energy than the combined output of every star in our galaxy. Currently, that's not engineering, that's mathematical speculation and imagination. Wormholes present identical issues. They might exist theoretically, but if one formed, it would immediately collapse. Anything attempting passage would be torn into molecular strands by gravitational forces. So right now, we're limited to crawling through space. Even if you somehow conquered the velocity problem, another nightmare awaits. Space actively tries to kill you. You'd face continuous bombardment from deadly radiation, temperature extremes oscillating between molten heat and absolute zero, and microscopic particles impacting your hull with the force of bullets. At merely 10% light speed, a dust speck could puncture catastrophic damage through your spacecraft. Then there's logistics: food, oxygen, mental stability. You'd require a vessel functioning as a self-contained society for millions of years, essentially a mobile civilization transmitting stories and culture through countless generations. Even after all that, their far future descendants would still be surrounded by identical empty blackness. It's not exploration, it's exile. But here's the thing: you don't need to chase Andromeda, it's chasing you. Andromeda is currently rushing toward the Milky Way at roughly 400,000 kilometers per hour. In approximately 4 to 5 billion years, both galaxies will collide and fuse into a single massive structure. Astronomers already coined a name for it: Milkdromeda. The night sky during that merger will be spectacular, millions of new stars scattered throughout the darkness. Don't get too excited though, you won't witness it, none of us will. By that era, our sun will be in its death throes. Earth will probably be uninhabitable. So technically, yes, Andromeda will reach us, but humanity will be extinct long before the show begins. Discussing Andromeda isn't about journeys, it's about comprehending scale. We exist in constrained circumstances. We quantify distance in meters, kilometers, miles, a daily commute, a vacation flight, maybe studying overseas for a semester. The universe operates on entirely different scales. Its measurements are so incomprehensibly massive, they cease feeling like actual numbers. You could achieve velocities beyond what humans can currently imagine, and the cosmos would barely register your movement. But that's what makes it profound. It provides perspective. It demonstrates that you're positioned on a fragile speck in an isolated corner of an incomprehensibly vast universe, yet somehow you're capable of observing another galaxy entirely. That carries significance. Here's something that consistently blows my mind. When you observe Andromeda, you're viewing light that departed 2.5 million years ago. You're genuinely looking backwards through time. Now reverse that concept. If some intelligent being in Andromeda pointed instruments at Earth right now, they wouldn't detect you. They'd observe our planet as it existed 2.5 million years ago, before cities existed, before humans evolved. Perhaps they'd notice early hominids crafting primitive tools, or perhaps just forests and prehistoric creatures. When we observe each other across galactic distances, we're separated by time as much as space. That's one of the strangest and most fascinating elements of physics. Let's examine those numbers again. The Parker Solar Probe, our fastest creation, would require approximately 4 trillion years to arrive. Even a hypothetical craft traveling at 10% light speed would still need roughly 25 million years. Achieve full light speed, which isn't possible, you're still facing 2.5 million years. Or simply wait about 4 billion years because Andromeda is steadily moving closer anyway. When you contemplate figures like these, you understand that space doesn't acknowledge human concepts of velocity. Regardless of your calculations, we're not making that journey. Even light requires millions of years to bridge that distance. So next time someone suggests, perhaps eventually we'll visit other galaxies, you can respond, maybe when physics stops enforcing its rules. You'll never reach Andromeda physically, but you can step outside tonight and observe it with your own eyes, a barely visible blur in the sky, faintly luminous against the darkness. That light traversed 2.5 million years through absolute emptiness just to reach your vision. That's not failure, that's connection spanning space, spanning time, spanning everything.